Could we kill a modern submarine with an underwater A-bomb? In theory, yes. But what would be the fatal range? Could the attack crew get away? Important changes have been made in the balance of world naval power. Emphasis has been placed on subs, long-range atomic subs, silent subs armed with nuclear missiles. Our need to know was urgent. So, an atomic bomb, secured within this water and pressure-proof steel shell, was lowered 2,000 feet below the surface of the sea in very deep water, and detonated to provide us with the answers. This was Operation Wigwam. D-Day, the 14th of May, 1955. H-hour. Officially, 12:59 and 59.884. Let's say 1,300 hours Pacific Daylight Time. Our location, 28 degrees, 44 minutes north, and 126 degrees, 16 minutes west. Approximately 500 miles west-southwest of San Diego. We are reviewing the shot from the command ship, the USS Mount McKinley. We are 10,000 yards from surface zero. Operation Wigwam was conducted by Joint Task Force 7 under the direction of the Chief of Naval Operations, acting as executive agent for the Joint Chiefs of Staff and the Atomic Energy Commission. Immediate control rested with the Task Group 7.3 commander, Rear Admiral John Sylvester, United States Navy, and the scientific director, Dr. Alfred B. Folk, marine physicist, with Captain Jack Laughlin as his deputy. These were the men who were finally responsible for getting the right answers from the Wigwam test. The physical phenomena produced by the deep detonation lasted but a few minutes. But in that time, we gathered important information. We learned what we needed most to know.
The successful outcome of Operation Wigwam wouldn't have been possible except for the early foresight of those responsible for the preliminary planning that began almost 5 years before the final experiment. The Hartwell Report in 1950, the Project Alias Report in 1951, followed in 52 by the Armed Forces Special Weapons Project, Pelican Report, and ad hoc committee reports, all contributed guidance to the planners of Operation Wigwam. The consensus of these reports was, in essence, first, that a requirement existed for a nuclear anti-submarine weapon at the earliest possible date, and second, that the prevailing uncertainties as to the lethal range of such a weapon against submarines and surface vessels were too great to permit an adequate evaluation of its effectiveness or of methods of its tactical use. The basic purpose of Wigwam was, therefore, to resolve these uncertainties so as to aid in the use and future development of nuclear undersea weapons. To this end, and after many evaluations of the test scope, in light of budgetary limitations, operational feasibility, and other considerations, a minimum test evolved with the following objectives. We were to determine and evaluate the response of 3 targets, submerged to the same depth, but at various ranges, to obtain information from which a prediction could be made of the maximum range at which lethal hull-splitting damage to a typical submerged target submarine could be assured. We were to determine the peak pressure and pressure time fields in water and in air. We were to evaluate the surface effects with particular regard to their influence on delivery tactics. We were to determine the equivalent yield of the weapon used, the dispersion of radioactive contaminants, and the oceanographic factors affecting transmission of the shock wave. The location for the Wigwam experiment was chosen for several reasons. From a purely scientific point of view, We wanted to create simple experimental conditions, avoiding any complications that might adversely affect our data. At Crossroads, we fired an atomic weapon at mid-depth of relatively shallow water. For Wigwam, the test depth was 16,000 feet, with 2,000 feet of water above the point of detonation. In addition, our test site was located within what proved to be a biological desert, far from sea lanes or land masses. In order to learn what a shock wave of such long duration would do to a submarine, we had to build special gauges, exactly similar devices in which the gauge variations would be smaller than the variations in gauge environment. Originally, it was planned to use actual United States submarine types for our experimental targets. However, this plan was rejected on the basis of availability, handling complexity, non-uniformity, and cost. Our need to compromise between an actual sub and a simple pressure gauge evolved the squaw. In concept, the squaw design possessed a composite of the most important structural features of the modern submarines of the world. The resulting targets were actually based on a 4/5 scale model of the SS 563 class prototype, but with interior framing. This target offered several advantages over any full-scale submarine available. The cost was approximately equal to that of preparing and outfitting a heavy fleet-type submarine. It had the advantages of simplicity for model scaling studies, structural uniformity for comparison of performance between the three targets, and relative ease in handling and submerging. Also, advantage could be taken of the fact that it was new construction by providing certain built-in features that could assure a resilient target for lethal range analysis. The squaws were built as 14.5-foot diameter, internally framed pressure hulls, having a collapse depth of 1,400 feet and fitted with the required submergence tanks. All material in the pressure hull was 1-inch high-tensile steel, carefully heated and rolled for this job. All steel for the targets was divided to provide matching plates for the three targets. In this manner, it was hoped that the finished submarines would be as nearly identical as good shipbuilding practice could achieve. The Long Beach Naval Shipyard did an extremely fine job in the construction. The overall bow to stern length was 132 feet, the extreme beam 20 feet, and the depth from superstructure to bottom of keel 23 feet. The final displacement of each target in surface condition was 425 tons. The final design limitations were imposed by the total weight that could be conveniently handled in a salvage operation. Control of the unmanned submarine targets was maintained through a manifold on the parent YFNB barges by feeding compressed air through 5 1 1/4 inch submarine-type salvage hoses. Each of the 5 hoses was connected in turn to twin sets of ballast tanks, port and starboard, aboard the squaw. A carefully planned series of tests was conducted to cover all phases of the final operation. Scale model tests of structural strength were held at Ganave Gulf, Haiti, by the Underwater Explosion Research Division of the Norfolk Naval Shipyard, and the David Taylor Model Basin from 1952 through late spring of 1954. The test data resulted in additional strengthening of the crown of the squaw hulls above the ballast tank. Other tests were conducted to study the effectiveness of cable bundling schemes and handling and towing methods. The squaws were supported by 4 2.5-inch die-lock chain connected through hawse pipes on the pontoons and around the squaws in special hawse channels. 8 80-ton submarine salvage pontoons supported each squaw. In addition to the 5 salvage hoses and heavy support chains, there were instrumentation cables connecting each squaw to its instrumentation barge. Tests were conducted with the hose and cable bundles to determine proper design to prevent tangling, to ensure airtight fittings, and to achieve a neutral buoyancy for the bundles. In January of 1955, the results of the experimental scale tests and theoretical investigations were presented by the participating agencies at a Wigwam planning conference held at the U.S. Navy Electronics Laboratory in San Diego. 2 major uncertainties still existed. First, the actual relationship between peak overpressure and range, and second, the overpressure required to rupture the pressure hull. It was decided to express lethality in terms of shock overpressures, and within the range of uncertainty of the shock wave parameters, position the targets to bracket the maximum and minimum kill overpressures. Final estimates resulted in establishing target positions at surface ranges of 5,200, 7,000, and 10,000 feet from surface zero. This placement would provide one target where lethality was assured, one where lethality was about 40% probable, and one where hull damage should not be expected unless something most unusual occurred. The spring of 1955 found the pre-operational phase of Wigwam hurrying to meet a sailing deadline. Project working areas had been made available by the Navy Electronics Lab, whose fine administrative support made it possible for all of the Wigwam project personnel to feel that they had a responsible base of operation within the San Diego area. As we entered the final weeks of preparation, project personnel and trailer-mounted equipment gathered from many sections of the country. Vans were fitted out by the Naval Ordnance Laboratory, the David Taylor Model Basin, and the Naval Research Lab, and driven across the country from their bases in the Washington, D.C. area. The Edgerton, Germershausen, and Greer trailer from Cambridge, Massachusetts, the Armor Research Foundation trailer from Chicago, the Sandia van from Albuquerque, and the Navy Radiological Defense Laboratory trailer from San Francisco, all gathered at either the Naval Repair Facility dock area or at the Naval Air Station, North Island, prior to loading for the cruise to the operating site. One of the major reasons for the decision to use the large YFNBs as floating laboratories was to allow the trailer-mounted vans and project shacks containing recording equipment to be put aboard as completely integrated working units. It was essential that the full electronic story of event happenings be recorded on the surface in case we lost the squaws as a result of the detonation. So many gauges installed in the engine and battery compartments inside the squaws sent their signals through the cable bundles to the recording instruments aboard the YFNBs. Since the YFNBs would be stationed in the array relatively close to surface zero, it was decided to evacuate all personnel prior to H-hour and recover the recorded data as soon as possible after the event. In addition to the instrumentation located within the squaws, a variety of gauges were installed at intervals on and from the various units of the array. On YFNBs and in M-boats, strings of gauges were prepared to go over the side several hours before the event. Full photographic coverage of the surface effects was provided by batteries of manned and unmanned cameras located on the command and support vessels, on the 3 YFNBs, in 3 specially modified C-54 aircraft, and inside the squaws themselves. Some of the projects required permanently manned stations during the test, so their recording positions were stationed aboard the various task group ships. Early in May, and several days before D-Day, the first elements of the task group left port for the rendezvous area. A few days later, the faster ships left San Diego. Task Group 7.3 represented an interesting composite group of naval vessels, all having an essential part in the overall operation. The command ship, the USS Mount McKinley, and the weapons ship, the USS Curtis, were both veterans of other atomic tests. In addition, the Wigwam support family included the aircraft carrier USS Wright with her complement of AD-5Ns and Marine helicopters to provide search and taxi service. The 2 LSDs that served as a haven in heavy weather for the School of Overworked M-boats, and the 2 YAGs supporting the radiological survey and washdown studies. Important missions were also assigned to fleet tugs, ASRs, ARSs, LSTs, and a group of 8 destroyers that formed the perimeter security guard. Wigwam air cover was furnished by the Navy air elements from San Diego and the Air Force photographic aircraft from Albuquerque. The major operational element of the task group, the array itself, was a strange-looking floating blast line with its weapon barge, its 3 squaw target units, and auxiliary craft. It was 30,000 feet long when finally assembled and in tow by a single fleet tug, the longest towed array in naval history. This practically perfect array line was assembled during the sea trials off the coast of San Clemente Island in January of 1955. We enjoyed nearly ideal weather conditions. However, in May, the story was different. The weather was far from ideal. In fact, it exceeded our most pessimistic expectations. At the identical stage of the actual operation, D-2, the final array looked like this. The wind increased to 15 knots, and the sea began to pile up. Weather already caused a 3-day postponement in our test schedule. We had already lost the supporting pontoons for Squaw 29, resulting in its final use as a surface target. Consequently, a readjustment of the positions of all targets was made to ensure an adequate bracketing of the lethal range with only 2 submerged targets. This resulted in a final planned positioning of targets at surface ranges of 5,400, 8,200, and 11,400 feet. D-1 brought no improvement. We experienced a steady wind of 20 knots with gusts to 24. Sea and swells were totaling 10 to 15 feet high. Submerging the 2 remaining squaws was much more difficult that day than on any of the previous trials. Ideally, the submergence operation worked like this. The squaw took on ballast until it settled stern heavy, clearing the pontoons, sinking to the length of its 4 chains, 250 feet, below the surface. The supporting pontoons were then positioned directly over the squaw. The severe wind and sea conditions caused considerable bending of the array between the inner and middle targets. The actual distances of the targets at the time of detonation were 5,200, 7,300, and 11,000 feet, respectively, from the weapon support barge. This uncontrolled modification of surface distances proved to be fortunate in that it resulted in the second target receiving severe but not fatal damage, an ideal position for the study of target response at incipient lethality. Our scientific test program was organized into 6 main areas of responsibility: radiological and oceanographic investigations, target response and hull damage mechanism, timed and untimed technical and report photography, timing, firing, and communication support, weapon procurement and placement and evaluation of its performance, and measurements of free field pressures and other transient underwater and surface investigations. Notice the cloud chamber effect and the focusing of the reflected shock wave. This latter phenomenon was caused by the local valleys and hills in the sea floor. In at least one area, 15,000 feet from zero, the water was strongly whitened, indicating pressures in the neighborhood of several hundred pounds per square inch, about that to be expected at 10,000 feet, and enough to cause the collapse of light-hulled submarine. At other places, the bottom reflected shock appeared to be missing completely. At the Mount McKinley, 5 miles from zero, the bottom reflected shock was several times as intense as the direct shock wave. The initial spray dome, caused by the arrival of the primary shock wave, reached a maximum height of 147 feet at 2.4 seconds after detonation. The second dome, formed at approximately 2.5 seconds, accompanied by individual plumes, reached a height of 800 feet in about 7 seconds. 2 well-defined plume formations occurred. The first plumes reaching a diameter of 3,100 feet and a maximum height of 1,410 feet, 19 seconds after detonation. The second well-defined plume reached a height of 770 feet, 38 seconds after detonation. The outfall and descent of the material in the several plumes resulted in a well-defined base surge, about 640 feet in height and extending outward about 4,800 feet. The great mass of water thrown into the air resulted in surface waves that were about 2.5 times the maximum height predicted. A well-defined breaking surface wave was first observed coming out of the base surge at about 1 minute. This quickly became stable. The YFNB-12, at a range of 5,500 feet, rose and fell a distance of 40 feet. This resulted in a product of range times height of 220,000. The maximum product predicted was 80,000. These waves were completely undetected at the task group elements at a range of 5 miles, except that they showed beautifully on one surface search radar, which was temporarily out of adjustment. It had been knocked out of service by the shock wave, and on being returned to service, the gain was set high, so that strong sea return, modulated by these waves, covered the scope face. About 15 waves were visible, with wavelengths ranging from 5,000 down to 900 feet. The maximum energy appeared to be in the 1,800-foot region. These waves could have serious implications in the case of detonation of thermonuclear weapons on or under the surface of deep water. The seismic shock was easily detected all over the world. The Coast and Geodetic Survey reported the shock as an earthquake at 1300 Pacific Daylight Time on 14 May, with an epicenter about 15 miles from surface zero. The most probable position of the shot has been determined by task force navigation to be 28 degrees 44 minutes north and 126 degrees 16 minutes west, with a probable error of 1 minute of arc. At H hour plus 8 to 10 minutes, The shock wave hit the mainland of Lower California. At H+10, the SOFAR equipment at Point Sur, California, received the first shock wave. At 13:12 Pacific Daylight Time, a Greek ship just off the Golden Gate radioed the Coast Guard asking, "Has San Francisco just been hit by a severe earthquake? We have been badly shaken, but are all right and will return to render assistance if needed." At H+32 to 34 minutes, the Kaneohe station in Hawaii recorded the sound of the Wigwam detonation. And about 42 minutes later, Point Sur received a beautiful echo from the Hawaiian Islands. In fact, separate echoes from each of the islands in the group. Just to top the story, the Kaneohe station also recorded fine echoes from the California coast and from the Gulf of Alaska. The fallout and contamination resulting from the shot presented an ephemeral problem only. The major plumes were contaminated, but this material was present in a very large mass of water and for the most part returned to the ocean surface within a minute. No ship associated with the test received any accidental contamination. The converted Liberty ships, the YAG-39 and the YAG-40, transited the radioactive area. All transits were not completed as planned due to a long train of events triggered by minor shock damage to the YAG-39, which immobilized her for about 4 hours. At H+17 minutes, YAG-39 received a fallout reading of 400 Roentgens per hour, 5 miles from zero. An effective washdown system reduced this level to a maximum reading of 150 milliroentgens per hour on deck. The former amount of fallout could have produced casualties if the ship had remained immobilized or if the personnel had lacked the protection of a shielded control room. The radiological condition of the surface water in the first 13 minutes is not known by direct measurement. However, some of the dosimeters placed aboard the weapon barge were recovered. 4 of these gave good readings and were closely grouped around 3,600 Roentgens. Not one dead or stunned fish or mammal was observed from any task group ship, boat, or aircraft. The monitoring program of the California fish canneries has produced only 1 contaminated fish, and that proved to be a Japanese import and probably a result of Castle. This industry took the attitude that if Scripps Institution of Oceanography had determined the place for the test, there was no need to worry. A quantity of dye was placed aboard the Zero barge to aid in zero location, and anchored skiffs were positioned to provide absolute coordinates of motion and drift of the contaminated area after the detonation. The total contamination of the surface water appeared to represent about 1/3 of the explosion debris. Contaminated water was found at depth and followed for several days. This radioactive material appeared to be in thin layers, concentrating at a depth corresponding to the average density of the entire water column from the explosion depth to the surface. The stability of these layers appeared to be high and resulted in a concept of ocean structure resembling a pile of undulating sheets. The water of the mixed column subsiding to its equilibrium depth and then spreading out between the appropriate layers of stable water. By D+10 days, no area was found to read greater than 0.2 milliroentgens per hour, 3 feet above the surface. By D+40, no surface area was found reading greater than 1/100th of a milliroentgen per hour, 3 feet above the surface. By this time, the center of the largest area was approximately 120 miles west of 0 point. From a purely tactical point of view, radioactive fallout was most serious in the plumes and base surge and was probably dangerous about 1 mile upwind 2 miles a crosswind and several miles downwind. An operating washdown system effectively eliminates this danger. Except for a vessel immobilized in the contaminated surface water during the first very few hours after a detonation, no tactical hazard exists. The immediately observable results of the test regarding the submarine targets showed that Squaw 12, the closest to zero, was sunk. Squaw 13 was still intact with no flooding, and Squaw 29 was intact on the surface. Squaw 13, while intact, could not be surfaced and was subsequently lost during the 500-mile tow to the salvage site. For 300 miles, this target was towed by the instrument cables alone. Flooding of the main compartments of Squaw 12 occurred in less than 3 seconds after shockwave arrival, probably within 20 milliseconds. Flooding of the bow cone occurred at 27 seconds, and final parting of the instrument cable occurred at 57 seconds after shockwave arrival. Thus, the crushed hull sank nearly 400 feet in 1 minute. In the case of the damaged but unruptured target, hull plating and stiffeners suffered compressive set strains of several thousand microinches per inch. Although the free field measurements would indicate pressures somewhat larger, the measurements made in the ballast tanks of this target indicated a maximum total pressure just equal to the designed collapse pressure of the hull. This pressure was reached within a millisecond, indicating a prompt achievement of equilibrium between the applied forces and the reaction motions of the pressure hull. This appears to argue against a delayed yield effect, but the magnitude of the excess total pressure required to rupture the hull appears to be in agreement with the predictions based on the delayed yield theory. Serious hull damage to shallow draft surface vessels should not be expected at ranges greater than 4,000 feet. Minor shock damage may be expected at ranges from 7,000 feet to several miles. Aircraft at any altitude should be safe at horizontal ranges in excess of 1 mile. The underwater pressure time field of the Wigwam burst was similar in most respects to that computed for 40 million pounds of TNT at ranges greater than 1,000 feet. The peak pressure in air above this burst may be computed from acoustic theory, but the air shock duration is about 10 times that of the water shock. In answer to one of our primary questions, when in the presence of a nominal 30-kiloton nuclear weapon detonated at a depth of 2,000 feet in very deep water, the Squaw target, when submerged to a depth of 250 feet, will be crushed when at a range of less than 7,000 feet. Based on the results of the Wigwam experiment, several recommendations may be made. First, using scaled explosions and targets, studies should be made to determine the safe and lethal ranges for various types of submarines and surface vessels. Second, previous estimates of optimum warhead yield and explosion depths should be reevaluated in the light of Wigwam results. Third, scaled experiments should be performed to extend and improve estimates of wave production by explosions. This could critically affect the testing and use of thermonuclear weapons. Fourth, a marked reduction of the hull splitting range for submarines should result from an increased collapse depth and other radical design concepts which should receive careful study. And fifth, should additional tests of this nature become necessary, the area used appears excellent from the standpoints of international and fishery relations. If anticipated, the weather and sea conditions are not prohibitive. to relate the Wigwam experiment directly to the problem of our continued national security. The scientific information obtained by this operation has contributed greatly to the design of systems for the defense against enemy submarines.
Of May, 1955. H hour. Officially, 12:59 and 59.884. Let's say 1300 hours Pacific Daylight Time. Our location, 28 degrees, 44 minutes north, and 126 degrees, 16 minutes west. Approximately 500 miles west-southwest of San Diego. We are reviewing the shot from the command ship, the USS Mount McKinley. We are 10,000 yards from surface zero. Operation Wigwam was conducted by Joint Task Force 7 under the direction of the Chief of Naval Operations, acting as executive agent for the Joint Chiefs of Staff and the Atomic Energy Commission. Immediate control rested with the Task Group 7.3 Commander, Rear Admiral John Sylvester. Could we kill a modern submarine with an underwater A-bomb? In theory, yes. But what would be the fatal range? Could the attack crew get away? Important changes have been made in the balance of world naval power. Emphasis has been placed on subs, long-range atomic subs, silent subs armed with nuclear missiles. Our need to know was urgent. So, an atomic bomb, secured within this water and pressure-proof steel shell, was lowered 2,000 feet below the surface of the sea in very deep water, and detonated to provide us with the answers. This was Operation Wigwam. D-Day, the
Pelican Report and ad hoc committee reports all contributed guidance to the planners of Operation Wigwam. The consensus of these reports was, in essence, first, that a requirement existed for a nuclear anti-submarine weapon at the earliest possible date, and second, that the prevailing uncertainties as to the lethal range of such a weapon against submarines and surface vessels were too great to permit an adequate evaluation of its effectiveness or of methods of its tactical use. The basic purpose of Wigwam was, therefore, to resolve these uncertainties so as to aid in the use and future development of nuclear undersea weapons. To this end, And after many evaluations of the test scope in
the United States Navy, and the scientific director, Dr. Alfred B. Folk, marine physicist, with Captain Jack Laughlin as his deputy. These were the men who were finally responsible for getting the right answers from the Wigwam test. The physical phenomena produced by the deep detonation lasted but a few minutes. But in that time, we gathered important information. We learned what we needed most to know.
The successful outcome of Operation Wigwam wouldn't have been possible except for the early foresight of those responsible for the preliminary planning that began almost 5 years before the final experiment. The Hartwell Report in 1950, the Project Alias Report in 1951, followed in 52 by the Armed Forces Special Weapons Project